Okay, so if you're working in, say, construction or electrical design, you probably look at circuit breakers and think, okay, that's the ultimate safety net.
Right.
They protect the wiring, protect the equipment from overload. But sometimes, especially when we're talking life safety, well, the code actually insists you override those standard protections
I
completely.
Yeah, and that's exactly the paradox we want to explore in this deep dive. When it comes to installing a fire alarm system, the stakes are just incredibly high. And those traditional protections, the ones designed to save copper wire or prevent a motor burnout, they can actually become a liability.
Oh, so
Well, a single failure point, maybe even just a nuisance trip from one of those standard breakers, could lead to false alarms, sure, but also huge property damage, or worse, a failure to alert people when it really matters.
so today we're really digging into these super specific, almost kind of military-grade requirements that govern fire alarm wiring here in Canada. We're pulling from the key sources, the Canadian Electrical Code, the National Building Code, specifically the Alberta edition, which often leads the way, and the INU LEC-524 installation standard.
Exactly. And our mission today isn't just to read off a checklist. We want to get behind the why of these rules. Unlock the philosophy. We'll look at the big differences conventional versus addressable systems, Class A versus Class B redundancy, and crucially, why the engineer's focus shifts so dramatically. It moves away from just protecting equipment.
Towards guaranteeing reliability, even when things are going very, very wrong.
Precisely. Reliability under total duress.
Okay, sounds good. Let's unpack this. Where better to start than the absolute basics? The wires themselves, the physical conductors. What does the CE code say about the actual cable you're running?
Right, reliability starts right there with the material. Conductors have got to be copper. That's the baseline. The only real exception you'll see is optical fiber, and that's specifically for data links, usually between different control panels or major system components.
Okay. Copper and insulation.
Yep, insulation's got to be rated for a minimum of 300 volts. That gives you a safety margin, even though most fire alarm systems operate at much lower voltages, like 24 volts DC.
And I see there are strict minimum wire sizes too. That
Yeah.
seems, pretty standard for safety, but why the difference between pulling individual wires versus using cables?
Yeah, that comes down to physical durability during the installation process itself. If you're pulling individual conductors into a conduit or raceway, the smallest you can go is number 16, AWG, American Wire Gauge. But if those conductors are already part of a cable, maybe two or more conductors bundled with a protective jacket or sheath, or if they're just being laid into a raceway, not pulled under tension, then the minimum drops a bit to number 19, AWG. The thinking there is that the cable jacket or the gentle laying process provides some inherent physical protection.
Got it. Okay, now let's talk separation. This feels like one of those really fundamental rules that sets fire alarm wiring apart. This independence mandate. Fire alarm circuits have to be installed completely separate from all other wiring. Why is that so critical?
It's all about fault containment. That's the core idea. You absolutely do not want something going wrong in, say, a regular lighting circuit or a receptacle circuit like a short circuit or some electrical noise, a transient event. You don't want that interfering with the critical life safety system.
Because they need their own path.
Exactly. The fire alarm conductors have to run independently. That means dedicated raceways, dedicated cables. Keep them separate.
Okay, but there must be some exceptions, right? Otherwise, how does the main fire alarm panel even get power?
Right, right. The code has to be practical. There are very specific, limited exceptions. It allows connections for the essential stuff, the power supply feed coming into the panel, obviously. Connections to what we call ancillary control devices, things like magnetic door holders that release on alarm, or relays to shut down HVAC systems.
Makes sense.
And also communication circuits, like links to the fire department monitoring station. But that's pretty much it. If it's not directly serving that core life safety function, it needs to be kept electrically and physically separate.
And this idea of physical protection, it even changes based on the building itself, particularly in non-combustible construction.
Absolutely. If the building structure is designed to resist fire for a longer period, think concrete and steel buildings, then the wiring supporting the life safety systems needs that same level of protection to ensure it keeps working during a fire. So in those cases, the code requires things like totally enclosed metal raceways or cables that have their own metal armor or sheath, like an AC90 or tech cable.
What about non-metallic options?
You can use certain non-metallic conduits like rigid PVC conduit or EMT's non-metallic cousin, ENT, but only if they're completely embedded. They need to be buried in at least 50 millimeters, about 2 inches of concrete or masonry. That embedment basically provides passive fire protection for the wiring.
Okay, before we jump into the bigger systems and the really heavy-duty stuff, let's quickly touch on those smoke and CO alarms inside, say, an apartment or a house.
Mm.
The rules there also seem designed to make them hard to bypass.
Oh, definitely. Rule 32-200 is quite specific. Those alarms have to be powered from a circuit that also feeds lighting, or maybe a mix of lighting and regular receptacles.
Why tie it to the lights?
It's a simple, effective indicator. If that circuit breaker trips, your lights go out. And if your lights are out, that's a pretty clear sign that your smoke and CO alarms might be off too. It prevents them from being dead without you knowing.
And here we see that theme again, deliberately overriding standard electrical safety devices.
We do. First, you can't have a switch, any kind of manual disconnecting means between the alarm itself and the circuit breaker in the panel. No flicking a switch to silence it easily. And, this is the big one for electricians, generally, you cannot connect these alarms to circuits protected by GFCI's ground fault circuit interrupters or AFCI's arc fault circuit interrupters.
That's fascinating. Why ban GFCI and AFCI protection, which we normally want for safety?
Because, well, GFCIs and AFCIs, while great for preventing shocks and electrical fires from arcsing, they can sometimes be prone to nuisance tripping. They're sensitive. Imagine your fridge cycling on causes a tiny, harmless arc that trips the AFCI breaker while you're away on vacation. If your smoke alarm is on that circle,
It's dead for potentially days.
Exactly. So the code says no GFCI AFCI protection unless the smoke or CO alarm itself has its own built-in battery backup, an integral secondary supply. If it has the battery, okay, then the temporary loss of AC power from a nuisance trip isn't critical.
So we're choosing reliability of the primary power over the added protection of GFCI ASCI in most cases.
Okay.
Now, let's get to that really extreme example you hinted at earlier, that fire pump circuit philosophy.
Yes. This is where the code makes its most stark choice. It's the ultimate commitment to the mission over the mechanism. Fire pumps, as you know, are crucial in larger buildings. They boost the water pressure for the sprinkler systems and the fire hose connections. Critical stuff.
And the wiring starts conventionally enough.
It does. The conductors feeding the fire pump motor have to be sized correctly, usually at least 125% of the motor's full load current rating. Standard practice.
But then the rules for protecting that circuit just diverge completely from normal practice.
They absolutely do. They vanish. The code, Rules 32.310 and 32.312, mandates two really critical, unusual things. First, the circuit breaker feeding the pump must be lockable in the closed or on position, and it needs to be clearly labeled. This is to prevent someone accidentally or maybe even maliciously shutting off power to the pump.
Lockable on-in.
Sure.
And the second thing,
This is the shocker. Neither overload protection nor ground fault protection is permitted in the fire pump circuit.
wait, we're talking about banning the very devices designed to stop the motor from burning itself out if it's overloaded, or from causing a potentially hazardous ground fault condition.
That's exactly what we're saying. Banned.
Well,
Prohibited.
What possible justification is there for accepting that risk? The risk of destroying the motor or creating an electrical hazard?
The justification is the fire itself. The code takes the position that the risk of the pump not running during a fire is far, far greater than the risk of the motor destroying itself. Think about it. If the pump is struggling to start under heavy load, or if there's a minor ground fault developing, normal overload or GF protection would trip the breaker instantly.
And if the breaker trips?
The pump stops. The sprinklers don't get the pressure they need. The fire hoses are useless. The fire potentially rages out of control, and lives are lost. So the engineering decision is brutal, but clear. It is better for that motor to run itself into the ground, to literally burn out and destroy the equipment, than for it to trip off and fail to supply water to fight the fire.
The equipment is completely sacrificial.
Completely. Mission success putting out the fire overrides equipment preservation entirely.
Wow. That's a fundamental philosophical shift from nearly everything else in electrical design.
Yeah.
Okay, so we've established the physical requirements, the conductor rules, this extreme anti-protection rule for fire pumps. Let's look at how these systems actually monitor themselves. How do they know if everything's okay?
Right, now we're getting into circuit design and this core concept called electrical supervision. This is covered under Rule 32.106. The basic idea is that the fire alarm control panel needs to know constantly that the pathways out to all the devices, the detectors, the pull stations, the horns, the strobes are intact. And the way it does this, fundamentally, is by requiring that every single conductor be independently terminated at the device it connects to. No shortcuts.
Independently terminated.
Yeah.
Why is that specific detail so important? It sounds simple.
It sounds simple, but it's crucial for how supervision works, especially in conventional systems. Imagine if an installer tried to save time by, say, twisting 2 wires together under one terminal screw at a detector base.
Okay.
Now, if one of those wires breaks somewhere upstream, the supervisory current the panel sends out might still find a path through the other wire via that shared connection point. The panel would think the circuit is fine, but it's actually compromised. A whole section of devices might not work in an alarm, but the panel wouldn't know until it was too late. Independent termination prevents that hidden failure.
Ah, I see. It guarantees that a break in any single wire will interrupt the supervisory signal for that specific path. Okay. Let's break down these conventional systems then. You mentioned they're common in smaller setups. Let's start with Class B. You called it the vulnerable workhorse.
Yeah, Class B is very common. It's simpler, generally less expensive to install. In a Class B circuit, all the devices, let's say smoke detectors, are wired in parallel along a pair of conductors. And the supervision relies entirely on a small device, usually just a resistor, called an end-of-line device, or EOL. It's installed physically at the very last device on that circuit loop.
So the panel just looks for the current passing through that resistor.
Pretty much. The panel sends a small, specific amount of supervisory current down the line. It expects to see that current flowing through all the devices and then through that specific EOL resistance value. If it sees that, it knows the path is complete and intact.
Okay, well, what's the vulnerability you mentioned?
The EOL device, or rather the single path to it, is the Achilles heel. If there's an open circuit anywhere along that pair of wires, maybe a wire gets cut, maybe a terminal comes loose, then everything downstream of that break between the break and the EOL resistor loses its connection to the panel.
So those devices are completely blind. They can't report an alarm, can't report trouble.
Exactly. They're offline, but the panel only knows there's an open circuit somewhere. It doesn't know which specific devices are affected. That's the big weakness of Class B.
And how does the panel tell the difference between a wire break, an open circuit fault, and an actual fire alarm event in Class B? Or maybe a short circuit?
Good question. We need to quickly define the 2 main circuit types here. You have initiating device circuits, IDCs. These connect to things that detect fire, like smoke detectors or manual pull stations. And you have notification appliance circuits, NACs. These connect to the things that alert people, like horns and strobes.
Okay, IDC for input, NEC for output. Got it.
Right. So on an IDC, if one of the initiating devices activates, like you pull a pull station, it essentially creates a low resistance path across the circuit, almost like a short circuit. This causes a sudden, large increase in current flow, much higher than the normal supervisory current flowing through the EOL. The panel sees that high current rush and immediately interprets it as an alarm signal for that zone.
Okay, so a short on the IDC means alarm. What if the short happens on the NAC, the Hornstrobe circuit?
Ah, that's different. If a short circuit happens on the NAC wiring itself, the panel recognizes this abnormal current flow, but it interprets it as a trouble condition, not an alarm. The notification appliances, the horns and strobes, are designed only to activate when the panel specifically tells them to during an alarm state. They don't initiate alarms themselves, so a short on their wiring is just a wiring fault that needs fixing.
Okay, so Class B works, but that vulnerability to an open circuit taking out downstream devices is, well, it's significant. What's the engineering solution to get around that EOL dependency?
That brings us neatly to Class A wiring. Class A is all about redundancy. Instead of the circuit ending at the last device with an EOL resistor, Class A uses a return loop. There's a second pair of conductors run from the last device all the way back to the control panel, creating a complete loop.
Ah, so no EOL needed.
Correct. No EOL device. The panel supervises the loop differently. The massive advantage here is fault tolerance. If a single open circuit occurs anywhere on that loop, a cut wire, again the supervisory current, and more importantly, the alarm signals, can still travel back to the panel via the alternate path provided by the return conductors.
So the panel would still know there's a problem?
Oh yes. It detects the open circuit immediately and signals a trouble condition, telling you the loop integrity is compromised. But, and this is the key, all the initiating devices or notification appliances on that loop remain fully operational. They can still report or activate as needed.
That's a huge step up in reliability. Okay, now let's shift gears to the more modern systems. Addressable systems. They use something called a data communication link, or DCL. How do these supervise the wiring without relying on that constant supervisory current and EOLs.
Right, addressable systems are fundamentally different. They're digital intelligence systems. Supervision isn't based on measuring a simple DC current flow. Instead, the control panel actively communicates with each individual device on the circuit. It polls them. Basically, it sends out regular digital messages like voltage pulses addressed to each specific device. Hey, detector 101, are you okay? Pull station 203, what's your status?
So it's like a constant roll call.
Exactly like a roll call. Each device has a unique address and responds back to the panel. If the panel pulls a device and doesn't get the expected response back within a certain time, it knows there's a problem either with the device itself or the communication path to it, and it flags a trouble condition for that specific device.
That sounds way more precise than just knowing a whole zone has a problem.
It is. That's one of the huge advantages. The panel can usually tell you exactly which device is in trouble or an alarm, pinpointing the location instead of just saying, trouble on zone 3.
Okay, so addressable systems use this polling. How do faults, like short circuits, show up in this DCL world? Let's take DCLB first. That's the version without the return loop ending at the last device.
Correct. DCLB is the non-redundant addressable loop, similar in wiring topology to conventional Class B. But how it handles faults is critically different. If you get a hard short circuit across the DCL wiring, unlike a conventional IDC where that causes an alarm, on a DCL circuit, a short typically causes a trouble condition.
Why trouble, not alarm?
Because the short circuit essentially kills the voltage difference, the potential needed for those digital communication pulses to travel reliably along the wires. The panel tries to pull devices past the short, but the signal gets corrupted or lost entirely. It can't communicate.
So it loses communication and reports that as a trouble.
Precisely. The panel knows it should be able to talk to, say, devices 10 through 20, but suddenly it can't get replies. So it flags a communication trouble, often identifying the approximate area of the failure.
Okay, that immediately brings up the next big topic, fault isolation. If one short on a DCL circuit can potentially knock out communication to a whole string of devices, how does the standard, like Qian ULC S524, ensure that a fault in one area doesn't take down the entire system or devices in other critical zones?
Yeah, that's a core principle in S524. The goal is absolute. A fault, whether it's an open circuit, a short circuit, or a ground fault occurring within one defined fire alarm zone, must not prevent the normal operation of devices in any other zone. Faults have to be contained.
So how do you achieve that with these DCL circuits? If you have DCLA, the one with the return loop, like conventional Class A, or DCLB, the single-ended one?
Well, with DCLA and DCLB, the simplest way to guarantee that zone independence is the same way you do it with conventional systems. You run completely separate physical DCL circuits for each zone you want to isolate. Zone 1 gets its own DCL loop, Zone 2 gets its own, and so on.
But that sounds like a lot of wiring, especially in a large building.
Yeah.
Almost negates some of the benefits of addressable.
It can, yes. Which leads us to the really clever solution. DCLC, Data Communication Link Type C. This is where the true power and efficiency of addressable systems often comes in. DCLC is specifically designed to allow a single DCL circuit, a single pair of wires often, to serve multiple zones while still maintaining that crucial fault isolation between them.
How does it manage that? What's the magic?
The magic comes in the form of specialized devices called fault isolators, or sometimes fault isolation modules. These are intelligent devices placed strategically along the DCL circuit, usually between zones or critical segments.
And what do?
They constantly monitor the voltage and current on the circuit segment they're connected to. If they detect an abnormal condition, specifically a severe short circuit, on the section of wire immediately downstream from them, they react incredibly quickly, usually within milliseconds, to electronically open the circuit at that point. They disconnect the faulted segment from the rest of the DCL loop.
Ah, so they act like automatic circuit breakers, but specifically for shorts on the data line.
Kind of, yeah. They contain the short. So imagine you have isolator 1, then zone 2 wiring, then isolator 2, then zone 3 wiring. If a dead short occurs in zone 2 between those two isolators, isolator 1 detects the short downstream and opens, preventing the short from dragging down the upstream part of the circuit going back to the panel. And isolator 2 detects the short upstream relative to it and also opens, isolating that segment. The result: Zone 2 might be offline due to the short, but Zone 3, past Isolator 2, remains fully powered and communicating with the panel because the isolators protected the integrity of the main loop.
That's pretty smart. It lets you run one long circuit but still chop it up electrically when things go wrong. Saves a ton of wire compared to running separate loops for every zone.
Exactly. That's the huge advantage of DCLC with fault isolators. Big reduction in wiring and installation cost, especially in complex buildings.
Now, the rules for where you put these isolators, they get really specific too, especially when dealing with fire separations, right? It's not just about electrical zones anymore.
No, it's about physical survivability, too. The code, S524 again, thinks about the building actively burning and coming apart. If you have DCL wiring passing through a fire separation that's rated for 45 minutes or more, like a solid concrete wall between major building sections, you have to install a fault isolator on both sides of that penetration.
Both sides. Why two?
Redundancy against physical destruction. And here's the really specific detail that shows the level of thinking. Those two isolators, on opposite sides of the wall, must be horizontally offset from each other by at least 400 millimeters, about 16 inches. And they can't be installed in the same wall stud cavity, even if offset vertically.
Okay, why the offset? What's the scenario they're worried about there?
They're worried about the fire physically breaching the wall at one point. If the isolators were directly opposite each other, a failure intense enough to destroy the isolator and wiring on the fire side might also conduct enough heat or cause enough structural damage through the wall to simultaneously destroy the isolator on the other side. The offset significantly increases the chances that even if the fire takes out one isolator, the other one, physically separated, will survive and maintain the integrity of the DCL loop on its side of the fire separation.
Wow, that's engineering around physical failure modes, not just electrical ones.
Okay.
Let's shift from fire barriers to, well, human behavior. There's a specific requirement for sweet fault isolators in places like apartment buildings or care homes. That sounds like the code acknowledging that people get annoyed by alarms.
It absolutely is. It's a pragmatic acknowledgement of reality, particularly in multi-unit residential buildings. That's Group B, Division 3 occupancies like apartments, or Group C like care homes in the building code classifications. False alarms happen. People get frustrated. Sometimes, unfortunately, an occupant might tamper with or damage a notification appliance like a horn or strobe inside their suite, maybe trying to silence it during a false alarm.
And if they damage it badly enough,
They could potentially cause a short or an open on the notification appliance circuit, the NAC, that feeds multiple suites or even a whole floor. That one act of frustration could disable audible or visual warnings for many other people.
so the code allows occupants to silence their own device temporarily, I think.
Yes, the National Building Code actually permits systems, especially in residential suites, to have a feature where the occupant can silence the audible alarm signal within their own suite for a period, usually up to 10 minutes. But the common area alarms and visual signals typically continue.
But to prevent malicious damage from taking down the whole circuit, we need these sweet isolators.
Correct. Suite fault isolators, specifically on the NAC circuits feeding into individual suites, are required in these occupancy types. They function just like the DCL isolators we discussed, but for the NSE power. If someone damages the device or wiring inside their suite, causing a short, the isolator feeding that suite trips, disconnecting only that single suite from the NAC. Everyone else's horns and strobes keep working. And crucially, to prevent tampering with the protection itself, these suite isolators must be installed outside the suite they protect, typically in the public corridor, and they need to be clearly labeled and visible. You can't hide the protection mechanism inside the area it's protecting from potential tampering.
Makes perfect sense. Okay, one last piece on the hardware side. Addressable systems are great, but sometimes you still need to connect older, non-addressable devices to them. Maybe a special sensor or a water flow switch for the sprinklers. That's where modules come in.
Exactly. You often have a mix of technologies. Addressable panels need a way to talk to these conventional or dumb devices. There are three main types of addressable modules that act as translators or interfaces.
Okay, what's the first type?
First is the monitor module. Think of this as the input translator. It's used to connect non-addressable initiating devices, things that detect a condition, to the addressable loop, the DCL. Common examples would be connecting the switch on a sprinkler water flow indicator, or a pressure switch on a dry system, or even a zone of conventional detectors to the main addressable panel.
And does the monitor module supervise the wiring to that conventional device?
Yes, that's a key function. The monitor module typically supervises the small loop of conventional wiring between itself and the end-of-line resistor placed at the conventional device, like the flow switch. So the addressable panel knows if that connection is intact.
Okay, monitor modules for inputs. What's next?
Next is the signal module, sometimes called a NAC module or relay module, though that term can be confusing. As the name suggests, this interfaces non-addressable signaling devices, the outputs, like horns, strobes, or bells, with the addressable panel. It essentially allows the addressable panel, using its digital DCL commands, to turn on and off a conventional NAC circuit powered separately.
Got it. So monitor for inputs, signal for outputs like alarms. What's the third type?
The third main type is the control module. This one is a bit different. Control modules are used primarily to interface the fire alarm system with ancillary building systems. Things like shutting down fans or closing dampers in the HVAC system, releasing electromagnetic door holders on fire doors, maybe unlocking certain exit doors during an alarm. It basically provides a relay contact, like a switch, that the fire alarm panel can operate based on its programming.
Okay, so it controls other building functions. What's the critical difference or caveat we need to remember about control modules compared to signal modules?
The absolute key difference is supervision. Control modules typically just operate an internal relay. They close or open a contact. They do not generally provide electrical supervision of the circuit or the equipment they are controlling. The fire alarm panel knows it told the control module to operate, but it doesn't inherently know if the fan actually shut down or the door actually closed.
So it's just sending a command, not verifying the result electrically.
Exactly. And because of this lack of inherent electrical supervision on the output circuit, control modules are strictly unsuitable for activating life safety notification appliances like horns or strobes. You must use a supervised signal module for those critical outputs. Using a control module for signals would violate code because the wiring wouldn't be supervised.
That's a really important distinction. Okay, let's wrap up with a couple of really practical, almost in-the-weeds wiring details that highlight these differences. Let's talk about splicing wires and junction boxes. There's a weirdly specific rule for conventional circuits. Only 2 wires per splice.
Yeah, it seems oddly restrictive, doesn't it? For conventional circuits, particularly Class B IDCs that rely on that EOL resistor for supervision, the rule generally limits you to only 2 conductors per splice point within a junction box, unless using specific approved multi-tap connectors, which are less common.
Why so strict? What breaks if you try and, say, twist 3 wires together?
It comes back to maintaining the integrity of that supervision current measurement. Remember, the panel is looking for a very specific resistance value through the EOL at the end. Every splice adds a tiny bit of resistance or potential inconsistency. If you start having multiple parallel paths or complex tap-offs within junction boxes using simple wire nuts, it becomes very difficult, if not impossible, for the panel to reliably distinguish between the correct EOL reading and potential fault conditions like opens or partial shorts. It muddies the water.
So the 2-wire rule keeps the current path clean and simple for the panel to monitor.
Precisely. It maintains that clear, single-series path needed for reliable EOL supervision.
But then we get to addressable systems, DCLB specifically, and there's an exception. Tap splices are okay sometimes.
They are, and it highlights the fundamental difference in supervision methods, because DCLB relies on digital polling individual communication with each device, rather than measuring a precise analog resistance value through a continuous loop. It's much more tolerant of variations in the wiring topology. As long as the digital signal can reach the devices reliably, the system works. So under certain conditions defined by the manufacturer and standards, DCLB systems are permitted to use tap splices, sometimes called T-taps. You can branch off the main DCL loop to connect devices. This is something strictly forbidden in conventional Class B because it would instantly wreck the EOL supervision.
So the digital nature allows for more flexible, tree-like wiring structures that conventional just can't handle reliably.
Exactly. It shows how the underlying technology dictates the practical installation rules.
Okay, this has been, well, a really deep dive. We've covered a massive amount of technical detail, but it all points back to ensuring these systems work when needed.
Absolutely. And the core takeaway for you, for anyone involved with these systems, has to be this. All these hyper-specific, seemingly minor rules, the minimum wire size, the need for independent termination, the exact placement of isolators with offsets, the splicing rules, they aren't just arbitrary. They form this quiet, almost invisible, critical foundation. They are what ensure the entire life safety system performs exactly as designed, even when the building around it and its standard electrical systems are failing catastrophically during a fire.
And thinking back to where we started, that fire pump circuit, Learning that it's deliberately designed to sacrifice itself to burn out rather than trip off by banning standard overload and ground fault protection
Yeah.
is profound. It forces you to think. It really makes you consider the broader implications of that kind of extreme engineering philosophy. Where else, maybe in medical devices, maybe aerospace, critical infrastructure, control systems, where else do engineers face that stark choice? Where failure is simply not an option and they have to deliberately override normal safety protocols to prioritize the mission, the ultimate goal, over protecting the equipment itself.
It definitely forces a recalculation of risk and priorities, doesn't it?
It really does.
Yeah.
Something to definitely mull over.